Okay, so on the bell work, I ask you, where does he have to jump? What answers did you come up with? Where are you going to press the jump key? At what time are you going to press the jump key? So I've given you 5 minutes and not one person can answer.
2.5.
Thank you. Very good. That's exactly right, at 2.5. Okay, so how do we figure that out? Well, you look at your parabola over here. Okay, where's the highest point? At 2, right? So we know it's going to take him 2 seconds, or units of time, whatever those units might be, but 2 of those to get to the top of the parabola, the highest point of that arc. And that's where he needs to be, at 2. But notice that we're on different measures down there. So what do we have to do? We've got to count back 2 seconds, right? So let's go back 1, which would put us at 3.5, and back 1 more unit would put us at 2.5. And that's the point where you need to press the key. I'm sorry. Well, it won't be on the video, but it was on there. Sorry. The projector was frozen. Okay, so let me show that one more time. So the 2, there's the highest point at 2 seconds. So you know it's got to be 2 seconds from this highest point. So you go back 1, and that's going to put it at 3.5, and you go back 1 more, and it puts it at 2.5. So you need to press that jump key right there at 2.5, and then he'll go up, and it took him 2 seconds to get up there, and it's going to take him, from this graph, 2 seconds to get down. So where will he land? .5, very good. So it'll take him 2 seconds. So from 4.5, 1 more is 5.5, and 1 more from there is 6.5. So there you go. And this is just a very basic parabola shown by a horse jumping. And just know that all parabolas are going to go up, go to a highest point and go down, or they can turn around the other way and fall down, hit the lowest point, and go back up. The point where both sides meet, whether they're upside down or right side up, that's called the vertex. Okay, that's a vertex. And the line, they're a mirror image of each other. Each side is a mirror image of each other. So the line that divides them, that you could fold it on, and they're a mirror image, that's called your axis of symmetry. So I'm a little ahead of myself, so let's look on the next paper here. So what we worked with was a parabolic shape of the horse's jump. And a parabola, it's the graph of a quadratic function. Okay, we can write that, and this is our algebra 1 part, as f of x equals ax squared plus bx plus c. And it says a cannot equal 0. And I'm going to talk about that in a few minutes. Okay, so this is the part we worked with in algebra 1. Okay, you might have seen it as y equals, but we're going to use those interchangeably. F of x, that just means we're working with the function, a function of x. Okay, so the essential understanding today is the graph of any quadratic function is a transformation of the graph of the parent quadratic function, y equals x squared. Okay, so basically what they want to show you is, let's work with this, and I'll show you a parent function of y equals x squared. Let me clear this first. So let's make a 3-column chart. Okay, and in this I'm going to have an x, an f of x, which we said is x squared, and then I'm going to have my output. But our output, we're trying to graph it. So let's just put it in a coordinate point form. So I'm going to say x, f of x. All right, so for the first one, I like to do the easy things first, right? Let's just pick 0. Well, what happens if I have f of 0? What that means is everywhere in this everything to the right of the equal sign, whatever that equation is, anywhere there's an x, replace it now with the 0. So we just have little old x squared, so we're going to replace x with the 0. And we know that 0 squared is just 0. So if I input a 0, my output's a 0. So we're going to plot that now at 0, 0, and that's our origin right there. Now I'm still not certain what kind of graph this is going to make or what it looks like, so let's just keep going. So I'm going to pick another easy number. Let's pick 1. Well, we know that f of 1 is equal to 1 squared, which is equal to 1. So I input 1, and I got an output of 1. So let's plot that one now. All right, so it's looking good. Well, it looks like it started at the origin and it went up. Let's see what it does to the left of that origin point. Okay, hopefully it'll go up too. So let's see. Let's put in a negative 1. So if I have f of negative 1, I'm going to get negative 1 squared, which is equal to a positive 1. So now I input a negative 1 and I output a positive 1. So let's graph that. Back negative 1, up 1, and now we're there. So I could almost say, yeah, that looks like that's going to be our origin, but let's pick one more point to be certain. Let's do 2. So f of 2 is equal to 2 squared, which is equal to 4. So we're going to have a 2 comma 4. So let's plot that one. Over 2, up 4, right there. And let's do it with the negative 2. Negative 2 squared is also equal to a positive 4. So we're going to input a negative 2 and output a positive 4. So let's plot that one. Negative 2, positive 4. Now I can say, yep, that's definitely going to be our parabola. And it's going to look something close to this. And it's always a curve, never a V. All right, and there it is. And guys, that is the parent function, y equals x squared, or, as we're doing most of the time now, f of x equals x squared. That's the parent function. So everything we do today is going to translate off this parent function. Okay, so let's say we have a different equation, and it's basically just taking and translating like we did before. What's our horizontal movement? What's our vertical movement? We're going to do the same things. What's a compression do? What's a negative number do? What does a stretch do? So those are the things we're going to work on now. But I just help you see this parent function is always going to look like this. The parent function is always going to be at the origin, have the vertex at the origin. Line of symmetry is right down that y-axis. There's our line of symmetry. There's our origin. Always, the vertex is always the origin. And know that it goes through 1, 1, and negative 1, 1, and 2, 4, negative 2, 4. Okay, and if you remember those things, you can always quickly graph it. And by the time we get through this chapter, you'll be able just to draw it without even thinking of it. It's like, oh, yeah, the parent function, I've got that. All right, so any questions about what the parent function is or what it looks like? All right, now we're going to add to the parent function. Okay, let me delete this. There we go. So now we're going to talk about the vertex form of a quadratic function. It is this: f of x equal a times x minus h squared plus k, where a cannot equal 0. Right? And the thing that makes the shape of this parabola bounce back up after it hits the vertex, that comes from the x squared. The squared part of it makes it bounce back up, right? Because when you square a negative number, if we go negative, it's going to turn it into a positive. So we are always going to be in this shape. The squared part makes it be the shape of the parabola. So what happens if we take that squared away, the x squared? Well, let's see. If I had y equals x squared plus 3, and I have, actually I'm moving ahead. Let me back up. Let me stick to our formula before I go on to that. Sorry. So the f of x equals a times x minus h squared plus k. A cannot equal 0. Let's do it right here on this one. What happens if a is 0? Just let me stick a 0 in there. So we're going to have f of x equals 0 times x minus h squared plus k. Well, whatever happens in here, squared, whatever number that becomes, we're going to multiply it against 0, which makes it all go away. We lose the squared part if a is 0, which means we just end up with y equals a number, or y equals something. We end up with a linear equation, whatever it may be. So we lose our parabola, our quadratic part. Okay? Quadratic just means you've got the x squared in it, right? We're gonna work with parabolas and squares. That's what you need to think when you hear the word quadratic. Now, if we memorize this formula, which we will have it memorized very shortly because we're going to use it in everything we do for this chapter. So what do we know? Well, a minute ago we said we had the parent function, f of x equals x squared. Well, how does that fit in with this big long equation? Well, I'm going to show you. What if I told you it does, but a is equal to 1, h is equal to 0, and k is equal to 0? Well, let's just plug those in and see what we get. So I'm going to say f of x equals a, which I said was 1, times x minus h, which I said was 0, squared plus k, which is also 0. Now let's simplify this. F of x equals x minus 0 is just x squared times 1 is just x squared, plus 0. There's your parent function. Okay? So a was equal to 1, h was equal to 0, and k was equal to 0. If you have this formula memorized, there's some really cool things that can speed things up for us. Okay? Before I erase that, were there any questions about that or how we proved the parent function there? All right. First of all, the a. We know from previous chapters here, the a is going to be our stretch or compression. If it's greater than 1, it's a stretch. If it's between 0 and 1, it's a compression. So when we stretch a parabola, think of this being a string, and we're going to take it and pull it up. What's going to happen? It's going to get skinnier. So a stretch is going to do this. It's going to get skinnier and skinnier. A compression, on the other hand, think of a big brick setting on a metal beam, and we're just going to lay it up there. It's going to start stretching it out further and further and further. Okay, so that's what the compression does. I shouldn't have said stretching out. Pressing it out. There we go. All right, so there's a couple of properties that happen from this. Your A value is going to tell you if you have a stretch or compression, and your H and K, well, H is your horizontal position of the vertex, and K is the vertical position. So let's see what that is. Well, in our parent function, f of x, we equal x squared, we said that h and k were 0. So that means my vertex is equal to h comma k, right? The horizontal and vertical. So I said it was 0 and 0. Was that true? When we graphed that, was the vertex at 0, 0? Yes, it was. So if you can get your equations and with this vertex form, you can quickly pick out your vertex. Be careful because you've got that negative sign in there, right? That's what makes it look like it's going the opposite direction when we start the translations, because you got the negative in there to begin with. So there's your vertex, and also this h value is your line of symmetry. Axis of symmetry, excuse me. And here we call it axis of symmetry. So if it was 0, well, there it is. So my axis of symmetry was x equal h, which in our h here was 0. So my axis of symmetry is x equals 0. Write down that y-axis. Okay? So those are the things you can tell from that formula. All right? And we'll use it a lot in the later parts. Today we're going to do more graphing. Okay. Any questions on this so far? All right. So here it is again, the parent quadratic function. We've done a bunch. So it's at the vertex of 0, 0 at the origin, over 1, up 1, over to the left 1 and up 1, and then 2, 4 and negative 2, 4. So there's that parent function. All right. If you know your line of symmetry, let me show this with a different. If you know your line of symmetry and you know you've got something, you found your vertex, we got our HK and got our vertex, and I've calculated this point, and I know this is my vertex. Well, if I calculate here, and that's 1 unit, then I can translate that or reflect it over here. And then if I calculate another value up here, then I know I can do the same over here. See, he is 2 units away. So from my axis of symmetry, that's what I'm using, I can go 2 units away and reflect that same point. Now I have my 5 points, which is what I'd like to have at least to graph a parabola. All right, so if you can get 1 point and you know your axis of symmetry and your vertex, you can just reflect those points on the other side. All right. So let's look at our first problem. What is the graph of f of x equals 1/2 x squared? So our first step, well, we already know from our formula that our h is equal to 0, we don't have an h value, and we don't have a k value. So we know right away that it's going to go through the origin. Our vertex is the origin. Our axis of symmetry is also right down that y-axis. So now, what do we have? That parent function, and it's going to be stretched or compressed by a factor of 1/2. What is that, a stretch or a compression? Compression, because it's between 0 and 1. So we have a pretty good idea that it's going to be like that parent function, but a little bit wider, right? So that's what we're expecting, but we have to graph it. So let's start by graphing your, there's an actual graph down here. Plot your origin right down there. And now you want to start your chart, and it's a 3-column chart where we do our calculations in the middle, and we end up with our point to graph. So if I input a 0, we already know that. We're going to get an output of a 0. If I input a 2, and guys, this is just a little math trick. If you want to work with whole numbers and you've got a fraction as your a value, choose all values that are multiples of that denominator. So that's a 1/2, so you want to look at 2. So for your x, use 2, 4, 6, 8. Okay, use multiples of 2. So, and they did just that. So if I input a 2 for x, I get x squared, which is 4, and 1/2 of 4 is 2. So I get 2, 2. So I'm going to come over here, and because I know my vertex and my axis of symmetry, I'm just going to reflect on the other side of my axis of symmetry this 2, 2 point. So if he's 2 units away here, he's got to be 2 units away there. So I like to put an x when I reflect, but you can do whatever you want. Okay. Now, so now I have 3 points. Now I'm going to calculate one more with the 4. So 4 squared is 16, and 1/2 of 16 is 8. So I'm going to graph 4 over 4 and up 8. And that is 1, 2, 3, 4 units away. So I'm going to reflect it on the other side of the axis of symmetry. 1, 2, 3, 4, right there. Now I have 5 points, and I can certainly graph that with certain that that's correct. Okay? So the vertex is 0, 0, axis of symmetry is x equals 0. And there's my graph. Okay? Any questions on that? Okay, flip your whiteboards over and let's work another problem together. What is the graph of f of x equal negative 1/3 x squared? Let's all graph this. F of x equal negative 1/3 x squared. Well, what's our h and k value? 0 and 0. So we know it's going to have a vertex of 0, 0. Remember, your vertex is just hk. Alright. Now, there's something I haven't told you about that we're going to find out here in just a moment. Okay, just toss it and doesn't work at all. Toss it and grab another. Thank you. So let's start our graph here. So we know we've got an origin of 0, 0. And we know it's not the parent function because we've got this negative 1/3. I'm going to give you a little hint. When the a value is negative, it's upside down. When a value is positive, it's right side up. So you could say the negative is a frown and the positive is a smile. Okay? So expect, because I've got a negative a value, that this is going to be going down somehow from the vertex. All right? So let's figure out how to do this. So let me get a graph up. Boom. So we have f of x equal negative 1/3 x squared. Boy, that didn't turn out very good, did it? And then I'm going to give my x f of x. All right, so let's put, we know our first value when we do 0, 0, it's going to be at the origin. All right, and if you're not sure, then just plug it in. 0, what is f of 0? Well, negative 1/3 times 0 squared. 0 squared is 0. Negative 1/3 times 0 is 0. So it's going to equal 0 in the end. So there's your, we know already that's our origin. So now let's pick another number close by our origin. Let's do 1. That's easy to work with, right? Or actually we've got a fraction and it's in thirds, so let's pick a multiple of 3. Let's just use 3. So we're going to have 3 squared, which is 9, and 1/3 of 9 is 3, and it's a negative, so it's going to be negative 3. Okay, so let's plot that. 3 and negative 3. Oh, looky there. So now we are going upside down. We know this is an axis of symmetry, so let's reflect that point on the other side. So he's 1, 2, 3 units away, so he has to be 3 units away here. So it's going to be right there. All right. Now let's get one more point. Let's see. Let's choose 6. 6 squared is 36. And negative 1/3 times 36. Well, what's 36 divided by 3? 12, and it's a negative, so it's going to be negative 12. So we're going to have 6, negative 12. So I don't know if mine's not going to go that low. It's going to be way down there. Okay, so it would go right here and there, way down there. So it's going to do something like this. Okay? If you use graph paper, you might change your units of measure. Like if you're doing all multiples of 3, change all your units to 3. Instead of 1, 2, 3, 4, 5, 6, do 3, 6, 9, 12. Okay? And that will save you some room. So, how did this change from the parent function? You would say, well, it reflected across the x-axis because it flipped over the x-axis, so it reflected over the x-axis, and it was also compressed by a factor of 1/3. Okay, so it's going to be a little skinnier and flipped upside down. Oops. All right. Any questions about that? Now, when you use the formula, you'll be able to graph that a lot quicker. All right, but for right now, let's just keep doing the. So here's, next week we're going to learn how to use the graphing calculators and do this, but you have to understand what all this means before you can go into the graphing calculators. So here's our key concepts so far. You've got the parent function right up here, and then it reflected with the negative parent function there. The a value, if it's positive, we've got a smile. If the a value is negative, we've got a frown. Okay, if we have a stretch where our a value is greater than 1, then it's going to be a skinnier parabola. If we've got a value between 0 and 1, like some kind of fraction, 1/2, 1/3, 3/4, it's going to start stretching outwards. Whoops. Okay, it's going to get flatter and flatter, like it's being pushed down on from the top. Okay, so if you have a positive a value, then you could say your vertex is at the lowest point of your parabola. So we call that a minimum value, the minimum value. Now, if you've got a negative a value and it flips it upside down, then your vertex becomes the highest point of your parabola. And we call that a maximum value. Okay. It's a little trivia there. So let's look at problem 2. Graphing translations of f of x equal x squared. Graph each function. How is each graph a translation of f of x equal x squared? So when we look at our first problem A, we've got g of x equal x squared minus 5. I'm going to stop here and say, well, g of x, we've been using f of x. Now why are they going to g of x? They can use whatever of x they want to use. The important thing is they're working with the variable x. It could have been f of x, it could have been g of x, it could have been z of x. Okay, it just means this is a function. And this function using x is different than this function using x, right? That's what they mean. So they're just getting you used to seeing functions written in different ways. I've seen some people do this, f of 1, f1 of x, and f2 of x. I've seen that too. But right now we're just using f and g. So now they've got a g of x equals x squared minus 5. Well, we could apply that formula. Well, let's do that first. So we knew the formula was f of x, which now we've got a g of x, equals a times x minus h squared plus k. Sorry, my pen's not too cooperative. Now, what do we have here? Well, we've got an x squared, so we have x and squared, and we have our k value, which is negative 5. So that means that our h must be a 0, And well, we know the k is what? -5. And our a value has to be 1 because there's nothing in front of the x. Okay. So we know right off the bat we've got a vertex at 0, -5. It's a smile parabola. It's right side up. And it's shaped exactly like that parent function. So let's look at the parent function right here. Right there in red is your parent function. So what this did is it's going to shift it down 5 units. Because our new vertex is right there, 0, -5. And it's the same shape. So a lot of students see this and they, let me see if I can do this. Not very good. I'm trying to trace this blue one. A lot of students think these are two completely different parabolas and they're the exact same. And I'm going to show you how. I've traced this and I'm going to move it up. See? It's sort of an optical illusion that your brain, because you're only seeing half of the red one, and it gets wider as it goes up, they think these are two completely different shapes, and they're the exact same shape. It's just an optical illusion. So what did we do? We took that parent function, and with that -5, x squared minus 5, it means h is 0, k is -5. So that's our new vertex, 0, -5. It shifted the vertex down 5 units. And there's no stretch or compression. So that's how it's a translation. So it took the parent function and shifted everything down 5 units. And that's what you would say. Any questions over that one? Okay, let's look at the next one. Now I have h of x equal, in parentheses, 4 minus x squared. Now, they threw parentheses in there. So we know we've got an a value again of 1, and our k value is 0. So our h value is what? What? It's x minus h. So what is h? 4. So h and our k equals 0, and our a is equal to 1. So now our vertex is h comma k, so 4, 0. So here's your parent function again in the red. Now our new vertex is hk, so 4, 0 right there. So what happened from this vertex to that vertex? It shifted to the right 1, 2, 3, 4 units. Was there any stretch or compression? Nope. Did anything else happen? Nope. Everything else stays the same. Okay, so see how to use our vertex form of our quadratics to help solve these quickly. Does anyone have any questions on this one? All right, you're awful quiet. That's either really good or really uh-oh. All right. Open your workbooks real quick to 4-1. And I want you to work, and this will be due first thing when you come back Monday, 4-1, problems 1 through 9. Okay, and I want you to work on that for the rest of the hour. And that ends this lecture. Any questions before I stop? Okay, thank you.